Good morning. Now, in our last lesson, we did talk about the solutions to a linear system of equations using a method that we call the Gaussian elimination method. The Gaussian elimination method is a direct method of solving the linear system of equations. Now, in this lesson, we shall consider the iterative methods. And here we shall look at two methods, what we call the Jacobi method and also the Gauss-Seidel method. Now, we shall consider a system of equations just like the one we have considered earlier using the Gaussian elimination. This system, which we shall call system 2.8, we can also write it in matrix form as 2.9. Or we can write it as ax plus b is equals to 0. Ax is equals to b. Like here, and define a, x, and b as before. Now, most iterative methods. Now, when we talk about iterative methods, we are talking about methods that approximates the solution of the system, the approximation methods. These are not direct methods. The methods that will give an approximation to the solution of the system by first taking the initial approximation, then you do another approximation to make your previous approximation better. You repeat the procedure and generate a system of approximations which eventually approximate the solution of the system. So in this case, we are saying that we start with a certain approximation that we will call the initial approximation. So this is where you take an approximation to the solution. You don't know what the solution of the system is, but you can approximate. For example, you can assume that x1 is 0, x2 is 0, x3 is 0, x4 is 0, x all the way up to xn are all 0. So you say x is equals to 0 is a solution. Once you have such an approximation, then you apply the procedure to generate now the solution. So you generate a sequence of vectors xk, starting with the x0 is 0, for example. Then you compute x1, which is assumed to be a better approximation than your x0, your initial approximation. You compute x2, x3, x4, and so on up to the point where you feel that you have best approximation to the solution of the system. So most iterative methods will involve converting our system into an equivalent system that takes the form x is equals to hx plus c, where h is an n by n matrix and c is a vector. Now the sequence of approximate solutions, vectors, is then generated by computing xk plus 1 for some xk. So given xk, starting with k is 0 for the initial approximation, you compute x1, then given the x1 that now you have obtained, you compute x2, and so on and so on. So we want to look at a linear system here, and then see how we can apply such a method that we are talking about to generate the solution of the system. So we shall start by doing this. From the first equation, we identify x1. From the second equation, we identify x2. From that equation, x3. The elements in the diagonal there. We shall make them the subject. So from the first equation, we can write 7x1 plus is equals to minus 2x2 plus x3 plus 6. From here, we can make x1 the subject, so we get 1 over 7 minus 2x2 plus x3 plus 6. We make x1 the subject from the first equation. From the second equation, we can make x2 the subject, and from the third equation, we can make x3 the subject. Once we have done that, we will obtain an equivalent system. We'll obtain a system now where we have x1 is the subject in the first equation, x2 is the subject in the second equation, and x3 is the subject in the third equation. And this one can be expressed in matrix form. So that now we have x1, x2, x3 on the left-hand side. On the right-hand side, we have this matrix. Notice that the elements in the principal diagonal are all 0, because these are the quantities that we made subject here. We made subject here, so that we were removing the elements in the principal diagonal from this side, from that system there. So that in this case, the elements in the principal diagonal are 0. Then we have this vector. So this one now we can write it as x is equals to hx plus c. You see h is this matrix here. X is the vector x1, x2, x3, and c is this vector here. So where h is that and c is that. So the iterative method is now expressed as xk plus 1 is equals to hxk plus c. This method, when we solve the equation using this kind of a method, we shall call it the Jacobi method. So to find the solution, we can set the initial approximation to 1, 1, 1. x1 is 1, x2 is 1, x3 is 1. Or we can even use 0. We can use any other value, not necessarily 1. Here we shall use x1. So from here, we shall write, when k is 1, we shall write xk plus 1 is 2. Then we have hx1 plus c. But now x1 here is equals to 1, 1, 1. Now we are using the superscript here, because we have also written that x is equals to x1, x2, x3. So we shall avoid to put the subscript here to avoid the confusion with this other x1. So in this case, we shall write x1 like that, meaning this is the first approximation. So that when we go to the second approximation, we shall also write x2. I want to use capital for some reason. So we shall write x2. This is the second approximation, which again will take the form x1, x2, x3. So these are the superscript will be used for the first approximation, second, third, fourth, so on. So in this case, we shall write x2 is equals to hx1 plus c. And x1, we have it here as 1, 1, 1. So we shall get x1, 2, x1, 2, x2, 2, x3, 2 is equals to, this is h, x1, then plus c. So when we work out, we get this equations, these values here. Similarly, for k is 2, we get, remember we are using the equation xk plus 1 is equals to h xk plus c. So when we set k is 2 here, then this will be 2 plus 1, which is 3. So we shall get x3 is equals to hx2 plus c. H remains the same, but now x2 is this vector here. This is our x2. So in the second step, that is what we shall be substituting to get x3. See that everything else has remained the same, only that now where we had x1, now we are replacing with x2, and we work out to get these values. And we can repeat this procedure many times. For k is 3, we get that. Then we substitute. K is 4, k is 5, and so on, until we get the solution. Now, see that we do not necessarily need to express the system in matrix form. We could have used here, if we could have taken the initial approximation, which we have taken x1 is 1, x2 is equals to 1, x3 is equals to 1, and we could have written here, this is x, the system now we have x1, 2 would be 1 over 7 into minus 2 x1, 1 plus this is not x1, this is x2, 1, x3, 1 plus 6. And this would have given us 1 over 7 into minus 2 times 1 plus 1 minus 6. Sorry, plus 6. Which we add minus 2 plus 1 plus 6 is 5. So this will give us 5 over 7. We can write x2 from the second equation here is equals to 1 over 8 into 4 x1, 1 plus 3 x3, 1 minus 36. And we work out x1, 1 is equals to 1, x3, 1 is 1. So we get 1 over 8 into 4. 4 times 1 is 4 plus 3 minus 36. And if we work out this is 29 over 8 minus 29 over 8. This is x2, 2. Remember, we have started with the first approximation, which is x1, x2 is 1, x3 is 1. Now we are getting a better approximation. From that equation here, we write x3, 2 is equals to 1 over 10 into 3x1, 1 plus 4x1, 1 plus 42. And this is x2, not x1. And x1, 1 was 1, x2, 1 was 1. So that we get, this is 1 over 10 into 3 plus 4 plus 42. And this will give us the solution as 1 over 10 plus 1 over 10 times 3 plus 4 plus 42. 3 plus 4 plus 42 is 49. This should give us 49 over 10 or 4.9. 4.9, these are now our solution. You see now we have x1, 2 is 5 over 7, x2, 2 is minus 29 over 8, and x3, 2 is 4.9. We can even express that in decimal, all those in decimal. Then now, so we have x1, 2, x2, 2, and x3, 2. this is equals to 5 all over 7 minus 29 all over 8 and 4.9. This is our solution after the first iteration, which is what we were obtaining after the first iteration here. These values here, which is we are calling x2. We can, after we get that, we can go back to our system again. Now from the first equation, if we go back to the first equation here, this one, now we can use the solution that we have obtained. X2 here is minus 29 over 8, and X3 is 4.9, and we get a better approximation to X1. So we write, using now these values, we write X1, 3, which is equals to 1 over 7, minus 2x2, 2, plus x3, 2, minus 6. I don't know whether it was minus or plus. It's plus 6. So we are now using x22 is minus 29 over 8, and x32 is 4.9. So we write 1 over 7 minus 2 times minus 29 divided by 8 plus 4.9 plus 6, and we get the value. We get the value of this. Then we go to the next equation and substitute again. In the second equation does not have x2. It has x1 and x3. So we shall be using 5 for 7 for x1 and 4.9 for x2. So once we do that, we shall get the solution in the next iteration. Now, the system, this solution or this procedure is repeated many times. If we repeat this for, like here, we've done it for 15 times. In the 15th iteration, we have 2 minus 2 and 4 as the solution, which is the solution of the system. Sometimes we may want to perform just a few iterations. We are given a system like this. We want to start with an initial approximation 1, 0, 0 and perform only 3 iterations. So you transpose the system to make x1 the subject in the first equation, x2 the subject in the second equation, and x3 the subject in the third equation. Get an equivalent system here. And from that, now we start with the initial approximation 1, 0, 0, which will give us this. Substitute here 1, 0, 0. You get that. When you get k is 2, the system will look like this. You substitute x1, 2, x2, 2, and x3, 2. This solution that you have obtained here, 3.8, negative 0.5, and 4.625. And the solution is obtained. This after the second iteration, 2.1, negative 0.86, 5, and 4.2062. Then perform the third iteration, and you get a solution. So basically, that's Jacobi method. Now, normally, when you are given a system of the form Ax is B, The Jacobi method can be obtained by first splitting the matrix A into the diagonal and off-diagonal parts. So we write A is equals to D plus L plus U, where D is the diagonal matrix, L is the row of triangular matrix. L is the row of diagonal triangular matrix, and U is the of diagonal upper triangular matrix. So when you are given a matrix like this, you separate, you remove the diagonal elements, then you have the upper and the lower part. So you have the diagonal matrix D, this is the lower triangular matrix, and the upper. See that these are off diagonal, not just the upper triangular matrix, so that you write A is equals to D plus L plus U. So the matrix system, or the system can then be obtained by replacing A with the three matrices, the sum of the three matrices D plus L plus U. Remember we had AX is equals to D. We are now replacing A with D plus L plus U. So we have X is equals to D. And we can write dx plus L plus U. X is equals to B. This is capital X there. This is B. So that we write dx is equals to minus L plus U, X plus B, and X becomes D inverse L plus U, X plus D inverse times B. This is negative here. So that when we write H X plus C, when we write our system as Hx plus C, then H will be equals to minus D inverse into L plus U, and C will be D inverse times B. So those are our matrix, the Jacobi coefficient matrix, the iterative matrix for the Jacobi method, H and C. Yeah. So in this case, the Jacobi method can be expressed as X is equals to Hx plus C, where H is that and C is that. Now we have the Gauss-Seidel method. The Gauss-Seidel method is obtained in the same way as the Jacobi method. We get to the iterative method almost the same way. But we realize that when solving the system using the Jacobi method, like now when we write the system, when we write the system such as the one we had in example 1, where we had x1 1 is equals to 1 over 7. Let me just check that equation here above. We had x1, so was a bit far. X1 this equation, like now this equation x1 or x12, when we are calculating x12, we get 1 over 7 minus 2x21 plus x31 plus 6, and we compute and we get 5 over 7. Remember, we had x1, 1 is equals to 0. So we were using 1. We are using the initial approximation as 1. x1, 2 is equals to 1. And x3, this is not 2, but x2, 1. x2, 1 is equals to 1, and x3, 1 is equals to 1. These are the initial approximations, so that we are saying x2, 1 is equals to 1 over 7 minus 2x2, 1 plus, this is x1, 2 is equals to 1 over 7 times 1 minus 2 x2, 1 plus x3, 1 plus 6. So x2, 1 is 1 from here. x3, 1 is 1 from here again. This is the initial approximation. So we compute x1, 2, we get 5 over 7. This one is assumed to be a better approximation than the initial approximation here. When we go to the second equation, notice that we have x2, and I want to look at what we have here. x2, 2 is equals to 1 over 8 times 4x1, 1 plus 3x3, 1 minus 36. Now, we are using x1, 1 is equals to 1 here, this value, for the Jacobi, so we multiply by 1. Here, 4 times 1, 3 times 1. Now, the idea of the Gauss-Seidel is that if we have already computed a value which is assumed to be a better approximation of x1, say we have already computed a value for x1. We had an initial approximation, yes, but we have computed another value here which we assume to be a better approximation. 5 over 7 is assumed to be a better approximation than the initial approximation here. So the question is, if we already have a value which is a better approximation to the solution than the one we have previously here, why are we using the older value here instead of the better approximation? So instead of writing x1, 1 here, we write x2, 1. So that we use this value. We use 5 over 7 rather than 1. This was an approximation, but we have already done another approximation which we assume to be a better approximation. So we assume that this one is a better approximation, so we use it here. Now x3, we have not computed any other x3, so we only have the odd value, so we're still going to use it. Once we have computed that, now the value of x2 will change, because now here we shall use 5 over 7, not 1. Everything else will remain the same. So the value of x2 here will change. Now, when we come to the last equation, we have x1, 1, x2, 1. Again, we have computed x1 and x2, which we are now assuming to be better approximations than the odd values here that we have taken approximation. So we are going to use them here. So we now use the updated values rather than the old values that we had initially. So the idea about the Gauss-Seidel is that once you compute a value and a value of a certain unknown, you don't go back to the old value that you had. You use the updated one. So that when we write a system like this one, when we convert this into a method of solving now the system, let me get some white space here. So once we have this system, hoping this one will give me what the space I require. Once we have this system here, we shall write something like now x using the Gauss-Seidel x1 k plus 1 is equals to 1 over 7 minus 2 x2k plus x3k plus 6 x2k plus 1 is equals to 1 over 8. This is the second equation. Now you have 4x1, but now x1 has been computed from the first equation here, so we shall use the updated value. We shall use the xk plus 1 that we have computed in the first equation. So we write 4xk plus 1. In the next one, x3 we have not computed any value, so we shall still use 3xk minus 36. When we come to the third equation, we are computing x3 k plus 1, which will be equals to 1 over 10. Now x1 we have the updated value from the first equation, so we write 3x1 k plus 1 plus 4. x2 we also have the updated value from the second equation, so we shall use it. x2 k plus 1 and then plus 42. So that in this case, you see that in the first equation, we are using x2k, x3k. These are the values from the previous iteration. In the second equation, we have xk plus 1. This is x1, and this is x3. So x1 k plus 1 is the value in the current iteration obtained here from the first equation. Now x3, we have not computed x3 yet in this current iteration because x3 will be computed in the third equation and we are in the second. So in this case, we use the value from the previous iteration xk. But when it comes now to computing x3k, we see that x1 has been computed in the current iteration, xk plus 1 here and here, x2k k plus 1, so we use them. So that in that equation does not have values from the previous iteration. We only have values from the current iteration. This is how the Gauss-Seidel method will look like. You see we have xk in the first equation. In the second equation, we have both xk plus 1 and xk. But in the third equation, we only have the values from the current iteration. This is basically the Gauss-Seidel method. So the idea is, if you have already computed a better approximation to a solution, you cannot go back and use an old value which you know it is not a very good approximation like the one you currently have. So in this case, you use the value in the current iteration. In that case, whenever it becomes available. So the whole idea about the Gauss-Seidel. Otherwise, everything else works the same way as the Jacobi. So we are saying that the Gauss-Seidel method can be obtained from the Jacobi method by using all available values from the current iteration, so that the method will take something like this form. And if we break it down in matrix form, we shall have the matrix A still being broken down into D plus L plus U, so that we have the system AX is equals to B still being expressed as D plus L plus U times X is equals to B. But here, notice that the lower triangular matrix will now be with D. We group D plus L, X plus U is equals to B. This is UX, and D plus L times X is equals to minus UX plus B, so that X becomes minus D plus L inverse times UX plus D plus L inverse times B. This matrix here is what we shall call H, and this now will be our C, which is now different from what we had in the Jacobi. So we shall take an example. We shall do an example of this method in the next session. Thank you for this.